Welcome to the Wireless Communication Technologies course. In this course, we'll start by learning the fundamentals of wireless communication. In other words, how data can be transmitted through the air using electromagnetic waves instead of physical cables. Next, we'll explore some of the most common wireless protocols, such as Wi-Fi and Bluetooth. Finally, we'll look at how to configure and set up wireless communication, covering basic parameters and settings. By the end of this module, you will understand how wireless systems enable communication between devices without the need of cables. Let's start by understanding the basics of wireless communication. A wireless network is simply a group of devices that exchange data through radio waves instead of physical cables. Data transmission happens using antennas, which send and receive electromagnetic signals. Common wireless devices include mobile phones, GPS units, and Wi-Fi enabled computers. Wireless networks come in different types, depending on range and use. So, in short, wireless communication allows us to share information seamlessly anytime, anywhere, without the limits of physical connections. Wi-Fi is a wireless communication standard used for local area, network, and internet access. Over time, Wi-Fi has evolved significantly, starting at just 2 megabits in 1997 to over 9 gigabits with Wi-Fi 6. Each generation improves speed, range, and efficiency with technologies like MIMO and dual band operation on 2.4 and 5 GHz. Today, Wi-Fi is essential for seamless wireless connectivity in homes, industries, and robotics. Bluetooth is a standard wireless protocol that transmits and receives data over 2.4 GHz band. It's designed for short-range, low-power, and secure communication between electronic devices. In robotics, Bluetooth plays several key roles. It enables remote control, allowing smart devices to operate mobile robots. It supports human-robot collaboration through wearable devices for real-time interaction. And it connects wireless sensors, helping robotic arms communicate efficiently during automation tasks. On the other hand, ZigBee is a low-power, short-range wireless protocol based on the IEEE 802.15.4 standard. It's designed for low data rates and energy-efficient applications, which makes it perfect for robotics and IoT systems. In robotics, ZigBee is ideal for battery-powered sensors thanks to its minimal power use. Its mesh networking capability allows devices to relay data across multiple nodes, extending coverage. It also supports thousands of devices in single network and ensures secure communication with AES 128 encryption. Overall, ZigBee is excellent for reliable, low-energy robotic communication. 5G is the fifth generation of wireless technology, succeeding 4G LTE. It delivers ultra-fast speeds, very low latency, and supports massive device connections across low, mid, and high-frequency bands. In robotics, 5G is a game-changer. Its ultra-low latency, under 1 millisecond, enables real-time robot control. Its high-speed data transfer supports AI-driven analytics and 8D video streaming. It also allows massive connectivity, linking thousands of robots or sensors in a factory. The Industrial Internet of Things, or IIoT, connects sensors, instruments, and devices with computers to support industrial operations like manufacturing and energy management. At the perception layer, sensors and robots collect real-world data. The network layer transmits its data wirelessly using Wi-Fi, Bluetooth, or other protocols. The processing layer handles data storage and analysis through cloud or data center services. Finally, the application layer enables functions like predictive maintenance, HV control, and energy optimization, all improving automation and efficiency. In robotics, implementing IoT brings both challenges and major benefits. On the challenges side, security risks and data management are key concerns, as sensitive industrial data must be protected. There are also interoperability issues between different systems and high setup costs for large-scale deployment. Despite that, IoT offers major benefits, including higher efficiency, cost savings, improve safety and better decision-making through data insights. In terms of application, IoT enables predictive maintenance, supply chain tracking, and energy optimization, as also remote monitoring, all essential for modern smart factories. Now, let's look at a hands-on example of setting up Wi-Fi on an ESP32 module. Step 1. Start by installing the ESP32 board package in the Arduino IDE, so the software recognizes the module. Step 2. Configure the ESP32 as a Wi-Fi access point, or AP mode, which lets other devices connect directly to it. Step 3. Then switch it to station mode, or STA mode, to connect the ESP32 to an existing Wi-Fi router. Finally, in Step 4, test the setup to confirm successful network connection and communication. In this first step, we will install the ESP32 board in the Arduino IDE. Start by opening the Arduino IDE on your computer. Then, from the top menu, go to File and then in Preferences. This is where we will add the ESP32 board manager in the next step, so that Arduino knows how to download and configure the ESP32 package. This setup allows us to program the ESP32 just like any other Arduino board. Next, we will add the ESP32 board manager so Arduino can download the correct files. In the Arduino IDE, go to File Preferences. At the bottom of the window, you will find the field labeled Additional Board Manager URLs. Copy and paste the displayed link. Then click OK. This tells the IDE where to find the ESP32 board for installation in the next step. After adding the ESP32 URL, the next step is to install and select the ESP32 board. Go to Tools, Boards Manager, search for ESP32 and click Install. Once installed, open the Tools, Board menu again and you will see several ESP32 options appear. Select the board that matches your hardware, for example, the ESP32 dev module. This tells the IDE which board configuration and libraries to use when complying and uploading the code. In this step, we'll configure the ESP32 as a Wi-Fi access point, so it can create its own wireless network. We start by including the Wi-Fi.edge library. Then define the SSID and password for our network. Inside the setup function, we initialize the serial monitor and call Wi-Fi.softapp SSID password. This starts the access point. Finally, we print a confirmation message and display the ESP32 IP address, so other devices can connect directly to it. In this step, we'll configure the ESP32 as a Wi-Fi station, meaning it connects to an existing router instead of creating its own network. We use Wi-Fi.begin to connect using your Wi-Fi credentials. The loop checks the connection status until it's successful, printing dots to show progress. Once connected, the program prints connected and displays the local IP address assigned by the router. This mode is perfect for connecting your ESP32 to a home or a lab network for IoT applications. Finally, let's test our Wi-Fi setup. Upload the code to the ESP32 using the Arduino IDE, then open the serial monitor to check the Wi-Fi connection status. If you are running in access point mode, look for the Wi-Fi network named ESP32 Robot Network on your phone or laptop and connect to it. If you are in station mode, the serial monitor will display the IP address assigned by your router, and this confirms a successful connection to your Wi-Fi network. Thank you for watching this video.